Bismillahirrahmanirrahim. Hello everyone. I hope you are having a wonderful day. I welcome you all in class of elementary number theory by David and Burton. Lastly, we have covered up to question number 19. In today's lecture, we will start question number 20. In this lecture, we will discuss this single question because this question has 6 parts. And actually, this question is related to the properties of greatest common divisor. So this is very interesting question. The first part of this question says, if GCD of A and B is equal to 1 and GCD of A and C is also equal to 1, then show that the GCD of A and BC is equal to 1. Throughout this question, I will use theorem 2.4 that can be stated as, let A and B be the integers, note both are 0. Then A and B are relatively prime, that is their GCD is equal to 1, if and only if there exist integers x, y such that their linear combination, this form, this form ax plus by is called linear combination of A and B. This linear combination of A and B is equal to 1. In simple words, two integers A and B are relatively prime if their linear combination ax plus by is equal to 1. For example, if you take A is equal to 3 and B is equal to 4, you know GCD of 3 and 4 is equal to 1. Now this theorem says that the linear combination of 3 and 4, that is 3x plus 4y, is always equal to 1 for every choice of x and y. So it is given that GCD of A and B is equal to 1. So we can find integers x naught and y naught such that A x naught plus B y naught is equal to 1. Say this is equation number 1. Similarly, it is also given that GCD of A and C is equal to 1. Again, we can find integers x1 and y1 such that the linear combination of A and C, that is ax1 plus cy1 is equal to 1. Say this is equation number 2. Now I have to prove that the GCD of A and BC is equal to 1. It means we will show that the linear combination of A and BC should be equal to 1. As this is the product form of BC, so we will multiply equation number 1 and 2 to involve the product B and C. So we multiply equation number 1 and equation number 2. So we have, this is the left side of equation number 1, ax naught plus by naught, and this is the right side of left side of equation number 2. And the right side of both equations is 1, so their product is 1 into 1, that is 1. So multiply these two factors, we have a square x naught into x1 ac x naught y1 up to so on is equal to 1. Taking common a from first three terms, we have a into ax naught x1 plus c into x naught y1 plus b y naught into x1 plus bc y naught into y1 is equal to 1. Here x naught, y naught, x1, y1, a, b, c all are integers. So their sum of product is also an integers. So this sum is surely an integer. So say this integer is equal to m, and this product y naught into y1, it is also an integer. So let this is equal to k. So the last expression, this expression becomes am plus bc into k is equal to 1. This expression shows that a and bc are relatively prime. It means their GCD is 1. That is required. Second part. In the second part, we have to show, given that GCD of AB is equal to 1, that is again A and B are relatively prime, and C divides A, then GCD of B and C is equal to 1. This is very interesting property. This property actually says if we have two numbers which are relatively prime, suppose my number is like 6 and 5. You can notice that 6 and 5 both are relatively prime. There GCD will be equal to 1. Now we know the divisor of 6 are 2 and 3. Suppose I take 3, as 3 divides 6. So this property says if we replace 6 by 3, that is the divisor, then again GCD of 3 and 5 will be equal to 1. So this property says if we replace A by the divisor C, then again the GCD of B and C is always equal to 1. Given that GCD of A and B is equal to 1, by theorem 2.4, we can find the integers x and y such that this linear combination is equal to 1. It is given that C divides A. C divides A. So by definition of divisibility, we can find an integer k such that we can express A is equal to k times C. This is the definition of divisibility. Substitute this value of A in equation number 1. So we have kc into x plus b into y is equal to 1. We take x inside the bracket and c take outside. So this becomes kx into c plus by is equal to 1. This shows that b and c are relatively primes. This shows GCD of b and c is equal to 1. C part. If GCD of AB is equal to 1, then if we multiply C with any of number, like in the question we are multiplying C with the first factor with A, then GCD of AC into B is always equal to GCD of C and B. We suppose that the GCD of CB is equal to D. Suppose this part has GCD equal to D. We show that the GCD of the left hand side is also equal to D. So consider GCD of CB, GCD of C and B is equal to D. By definition of GCD, as D is the GCD, so definition of GCD says D should divide both of the integers C and B. So D first divides C, similarly D divides the other number B. Now for both of these expression, we will use definition of divisibility. So we can find the integers k1 and k2 such that C can be expressed as D into k1, and from here B can be expressed as D into k2. Now substituting this value of C and B, say this is equation number 1 and equation number 2. Now consider the first part, that is GCD of AC into B. We have to show this GCD is equal to D. Take its left side, GCD of AC into B. Now substituting the value of C here. What is the value of C? Value of C is equal to D times K1. So this becomes A into D K1, and substituting value of B also, we have D into K2. By factoring out D, we have D times GCD of A into K1 into K2. Say this is star, and my left hand side is GCD of AC into B, that I have to show this side should be equal to only D. So if in star if we show the GCD of this number, this number GCD of AK1, AK2, if this is equal to 1, then it will complete the proof. It is given that GCD of AB is equal to 1. As it is obvious that A always divide A times K1. A times K1 means the first number of this expression. So by using part B, the part B was, this part says if GCD of AB is equal to 1 and C, this is part B. If GCD of AB is equal to 1 and C divides A, then we can replace A with C. Then GCD of B and C is equal to 1 also. Okay. We can replace as A divides A times K1, so we can replace A with number A K1. So by using part B, we can replace A is equal to A times K1 in this number GCD of A into B. So when you replace A with A K1, this becomes GCD of A into K1 into B, comma B is equal to 1. Say this is double star. Also from 2, what is 2? This is my expression number 2. B is equal to D times K2. Also from 2, B equal to D times K2. This shows that K2 divides B. For example, when you write A is equal to 2 times 4, this shows that 2 divides 8. This also shows that 4 divides 8. So this is the definition of divisibility. When you express one integer as the product of two integers, then it shows that this divisor is always divisible by the second. This is the Euclid theorem of divisibility. So again using part B, as now K2 divides B, so we can replace B with this number K2. So double star becomes A times K1 comma K2, GCD of A K1 A K2 is equal to 1. So put this value is in star. What is my star? This is my star. So replace this is equal to 1. This becomes GCD of AC into B is equal to D into 1, and D into 1 means D, that is required. Hence GCD of AC into B, GCD of AC B and GCD of C and B, this is equal to D, sorry, D here, it should be D here. That is, both have the same GCD. Last part, D part. If GCD of A and B is equal to 1 and C divides the sum of these two numbers, A and B, then GCD of A with C and GCD of B with C both are equal to 1. Given that GCD of AB is equal to 1, again by using theorem 2.4, we can find integers x and y such that we can write linear combination AX plus BY is equal to 1. It is given that C divides the sum A plus B. So by using the definition of divisibility, we can find an integer K such that this number A plus B, that is the dividend, can be written as C times K. Now from this equation, we will find the value of B. B can be written as Ck minus A. Substituting this value of B in equation number 1. So equation number 1 totally becomes in the term of A. So this is equal to Ax plus Ck minus A into Y is equal to 1. Substituting the value of B here. So after substitution, we obtain this equation. Now multiply Y inside the brackets, we have Ax plus Cky minus Ay. From these two terms, we take A as a common. We have A into x minus y plus C into ky is equal to 1. So this shows that this is the form of linear combination, and this linear combination is equal to 1. So this shows that the linear combination of A and C for the integers x minus y and ky is equal to 1. Hence GCD of A and C is equal to 1. That is, A and C are relatively prime numbers. Similarly, now we have to show that GCD of B and C is also equal to 1. This GCD, in this GCD, the number A is absent here. So now we eliminate the value of A from this equation. So from 2, when we eliminate a, we get a is equal to ck minus b. Now substituting this value of a in 1. What is 1? 1 is ax plus by is equal to 1. So substituting the value of a here. So this becomes ck minus b into x plus b into y is equal to 1. Multiply x, we have ckx minus bx plus by. From these two terms, we take b as a common. We have c times kx plus b into y minus x is equal to 1. This is again the linear combination of c and b, which is equal to 1. Hence, the GCD of BC is equal to 1. That is, they are relatively prime. E part. In E part, we have to show if GCD of A and B is equal to 1, if D divide the product AC and D divide the product BC, then D must divide number C. That is the common in both division. It is given that GCD of AB is equal to 1. There exist integers x and y such that we can write ax plus by is equal to 1. Say this is question number 1. It is given that D divides AC and D divides BC. This implies D divides the linear combination of AC and BC. We read the property of divisibility, which says if A divides some number B and A divides also another number C, then this property say A must divides every linear combination of B and C, Bx plus Cy. Every linear combination of B and C mean Bx plus Cy form. So we can use this property here. As D divides AC and D also divides BC, so according to this property, D must divide every linear combination of AC and BC. So consider this linear combination. D divides ACX plus BCY. This is the linear combination of AC and BC. Taking C as a common, we have D divides AX plus BY into C. From question number 1, AX plus BY is equal to 1. So substituting this value, the value of AX plus BY, we have D divides 1 into C. 1 into C means C as required. D divides C. Last part. In the last part, this is very interesting. In this part, we have to show if GCD of A and B is equal to 1, then the GCD of their squares is also equal to 1. To prove the result, we use part C, which says that if GCD of AB is equal to 1, then GCD of A into C, GCD of AC into AC and B and is equal to GC of CB. For this, firstly we show that GCD of A square into B and GCD of A into B square, these are both are equal. Then by using after proving this equality, we will use the final result. So to prove these two results, we will use property number C. Say this is star. Now to make the form of A square, we replace here C is equal to A. When you replace here C is equal to A, this becomes GCD of A square and B and is equal to GCD of AB. When you put here C is equal to A, this becomes A square, and on the right side this becomes A. So GCD of A square and B is equal to GCD of AB. But it is given that GCD of AB is equal to 1. It is given in this question. So substituting GCD of AB is equal to 1, this shows GCD of A square B is equal to 1. Interchanging A and B in double star. This is my double star. So when you interchange A and B, this becomes B square and this becomes A. Similarly, on the right side, this becomes GCD of, sorry, this is GCD, not G. This is GCD of B and A. GCD of B and A. As we know that GCD of AB is always equal to GCD of BA. In other words, if you interchange the numbers, their GCD will not be affected. For example, GCD of 3 and 4 and GCD of 4 3, both are equal. So this becomes GCD of B square into A is equal to GCD of BA, as GCD of BA is equal to GCD of AB, but GCD of AB is equal to 1. So this implies GCD of B square A is equal to 1. Say this is my triple star. Now we prove GCD of A square and B square, this is equal to 1 also. Now consider GCD of A square B, and again using the part C, we have, we can write A square as A into A. Now using this property, part C, if you replace here C is equal to A on both sides, this side become GCD of A comma B. So by using this property, we can write GCD of A into A is equal to GCD of C comma B. What is my C? C is A. So this is A. What is my B? Here my B is B square. So this becomes GCD equal to GCD of A B square. Above we have shown that GCD of A and B square is equal to 1. This is GCD of this is my GCD of A B square is equal to 1. From triple star, GCD of B square and A is equal to 1 means GCD of A and B square is also equal to 1. So using this fact, from triple star this is equal to 1, hence this implies GCD of A square and B square both are relatively prime, mean to say that this is 1. So this is, inshallah, in the next lecture we will discuss question number 21 of problem 2.3. If you find this lecture helpful, kindly like, share and subscribe my channel. See you in the next lecture. Take care. Allah Hafiz.